Okay, well, here we are back again. And actually, in the last lecture, we finished out officially all the material that was actually in the math section. And so I was kind of wondering what to do for our next couple lectures. We've got a couple more to go before the posting date for the first exam when we can go on to the physics section. Anyway, I decided that what we can basically do is work more examples. It really never hurts to get more practice. And there were homework problems in the textbook that we use in this class. Although, like I said, you don't really need it until we start the physics section. But we can work the problems that I didn't assign. And of course, I posted an image of the problems that I did assign. There's at the end of each chapter, there are what are known as parallel exercises, and that's because they're arranged in columns, column A and column B, and the corresponding numbered questions in the two columns are very similar to each other. And I generally assign people in the class to do the group B problems, or at least some of them, and the group A problems are the ones that have the answers in the back of the book. And so in future reference, if you're working on a B group problem and you get stuck, one thing you can do is try working the A group problem with the same number. And you can that way you can check your answer in the back of the book. And if you get the right answer, well, then that's probably how you do the B group problem of the same number. And so what I thought we could do for today's lecture is work over some of the, well, actually, there are only 10 of them, so we could do all of them. The A group problems for chapter 1 in our textbook. And again, I'll tell you what each question is as we come to it. And then if we still have some time left over, well, there are more problems I'm sure I can find. So, and these are basically along the lines of the same kinds of things we've been doing. It's just additional practice. And so number 1 under column A is, what is your height in meters? And also it wants to know in centimeters. Okay, well, let's see. We have all kinds of conversion factors available to us as part, sorry, I'm just looking for the sheet, as part of our math packet and also inside the cover of the book. And height is another form of length. And so looking down here at length, let's see, it wants it in meters. And, oh yeah, okay, there's one between meters and inches. So most of us probably know our height in feet and inches. And so if you can convert that to just inches, then you can go to meters using that conversion factor that's about halfway down the list in the length section. Sorry. Personally, my height is 5 foot 10 inches. And 5 feet, 5 times 12 is 60, plus another 10 inches would be 70 inches. Okay, so now that we've got 70 inches, we can use our conversion factor, which says that 1 meter is 39.4 inches. And you want inches on the bottom because that's the unit we want to cancel out. And you want meters on top because that's the unit we want to end up with. And so when you take 70 divided by 39.4, you get 1 point, okay, I'm going to put a decimal there so we can at least make it 1.8 meters. Okay, so that's two significant figures. If we want that in centimeters, we know that it's 1.8 meters. Sorry. And there's 1 centimeter for every 0.01 meters. this means, basically centi means 1/100th of a unit. So 1 centimeter is 1/100th of a meter, which in the decimal form you can normally write as 0.01. You can also write this as 100 centimeters per 1 meter, and both of those would work out equally because 100 divided by 1 is the same as 1 divided by 0.01. So if we have 1.8 divided by 0.01, we would get 180 centimeters. Again, if you put no decimal point in this number, that's two significant figures, which is what it should be because I started out with 70. And 39.4 is a conversion factor between the English and metric systems. So it's not infinite in significant figures. It has 1, 2, 3. The conversion factor between centimeters and meters, though, is within the metric system entirely. And so that's considered an exact number. So this has infinite significant figures. But again, we're limited to 2 because I quoted my height is only 70 inches. Okay, so that's number 1. What is the density of mercury if 20.0 cubic centimeters has a mass of 272 grams? Well, if you remember that density is mass over volume, then actually you could take the mass divided by the volume, and that's really all you have to do here because the question didn't specify any particular units for density. So, and remember, as I said, when we introduced density, any mass units over any volume units would be a density. In this case, they just happen to have given you grams and cubic centimeters, which would give you the standard units of grams per cubic centimeter for density. Okay, so 272 divided by 20.0 would be 13.6 grams per cubic centimeter. So that's really all you had to do for that one. Okay, 3. Okay, number 3 is what is the mass of 10 cubic centimeters of lead? For this, it might help to have our old triangle for density. Remember, density is mass over volume. And if we want the mass, then mass is going to be density times volume. We've got the volume here, but what we don't have is the density of lead. But like I said, density is a characteristic property of all pure substances. So you can look up the density of lead in any number of different places. It's in the textbook. Table 1.3 on page, 9, has a table of densities. But you could look it up on Google if you want to, and it should be the same number because, lead is lead. According to the table, lead has a density of 11.4 grams per cubic centimeter. And we have 10 cubic centimeters, and that's equivalent to being over 1. You notice that cubic centimeters cancel out, and we end up with grams. And 11.4 times 10 would be 114. 3 significant figures, 114 grams. It didn't specify units for mass, so you can leave the units, or you can leave the mass in whatever units you get. But you should read the questions carefully just to make sure, because if units were specified for, for the mass, then you might have to change this. Like if it said, what is the mass in kilograms? Then you'd have to change that to kilograms. All right, number 4. What's the volume of a rock with a density of 3 grams per cubic centimeter and a mass of 600 grams? Okay, so here's a density problem that involves finding the volume. So according to this table over here, if you want volume, you cover up the V, and volume is mass over density. So let's see, do we have the mass? Yes, we do. 600 grams, and that's over 3.00 grams per cubic centimeter. And that's going to be 200 cubic centimeters for the volume. Notice the grams will cancel with grams. Cubic centimeters are in the bottom of the fraction, which is actually the same as being on top. So that gives you 200 cubic centimeters. No decimal point in this one because you notice there was no decimal point for 600. 3.00, that's 3 significant figures. Because of the decimal point, the zeros at the end count. But 600 did not have a decimal point, so the zeros at the end don't count. That's only 1 significant figure. And so for the answer, it comes out to be 200, but just be sure not to put a decimal point at the end, because then it would be 3 significant figures, and it's supposed to be only 1 because of the 600. Number 5 says, if you have 34.0 grams of a 50 cubic centimeter volume of one of the substances in table 1.3, which one is it? So what we want to do here is find the density of this substance and match it up to one of the substances in the table. Because, again, density is a characteristic property of any given pure substance. So if you can find the density of this sample of the substance, it should be the same as the density of that substance in the table. Density is mass over volume. We have mass in grams and volume in cubic centimeters. That will give you grams per cubic centimeter for density, which is the standard unit that's listed in table 1.3. So let's go. 34.0 grams over 50.0 cubic centimeters. And that's 0.68 grams per cubic centimeter. And I don't even have to look because I remember this is the density of gasoline, 0.68 grams per cubic centimeter. If you look at the items in table 3, you'll see that everything there, I believe, everything there is a metal except seawater and gasoline, and water. Yeah, regular water, seawater, and gasoline. And of all of the things on the list, gasoline is the only thing that has a density of less than 1 gram per cubic centimeter. So gasoline it is. Gasoline is listed as 0.680. And actually, well, yeah, given the numbers that we have here, I should have written that as 0.680, three significant figures. So it would match the number in the table exactly. Okay, 6, what is the mass of water in a 40-liter aquarium? Well, this is a mass and density problem. We have the density of water in the table there, and it's 1 gram per cubic centimeter, so you should be able to remember that anyway. But anyway, according to the table here, if you want mass, it's going to be density times volume. And so mass is density times volume. We've got density in grams per cubic centimeter, but remember, cubic centimeters is the same thing as milliliters. So the density of water is 1 gram per cubic centimeter. It's also 1 gram per milliliter. And this makes it easier to convert the volume units because you have the volume of the aquarium in liters. Now all you have to do is change that to milliliters. So the volume of the aquarium is 40 liters. And there are 1,000 milliliters per liter. So that means the volume of the aquarium is 40,000 milliliters. So now we can take the density, 1 gram per milliliter, times the volume, 40,000 milliliters, which would be 40,000 grams. Now, that wasn't so hard. They did not specify any units for the mass, so you can leave that in grams. But it wouldn't be unusual in a case like this where the mass is so large if they perhaps ask for the mass in kilograms. So if you have 40,000 grams, you would multiply that by 1 kilogram for every 1,000 grams, and you would end up with 40 kilograms. Because as it works out, actually, the density of water is 1 gram per milliliter, which is actually the same as 1 kilogram per liter. So the density of water, when you're dealing with small amounts, you can think of it as 1 gram per milliliter. With larger amounts, you can think of it as 1 kilogram per liter. And so 40 liters, 40 kilograms, which is what we found the hard way down here. Okay, well, 7. A 2.1 kilogram pile of aluminum cans is melted and then cooled into a solid cube. Okay, so essentially what they're saying here is we've got 2.1 kilograms of aluminum. And they want to know what is the volume of the cube. Okay, so what would be the volume of the cube? Again, this is a density problem. Density is mass over volume. And let's see, it wants to know what the volume is. Volume is mass over density. So let's show you what we have for mass. We've got the mass in kilograms, and the density of aluminum, if you go to the table or Google it, is 2.70 grams per cubic centimeter. Okay. So we've got the density in grams per cubic centimeter. We've got, excuse me, the mass in kilograms. Um, 2.1 kilograms, and there are 1,000 grams per kilogram. Kilograms cancel. So we get 2,100 grams for the mass. So this is going to be 2,100 grams divided by 2.70 grams per cubic centimeter. Grams will cancel, and notice cubic centimeters is in the bottom of the fraction, which is the same as being on top. Whoops. 777.8 sorry, cubic centimeters. Sorry, okay. Another question that might occur, this one is actually not in the book, but I decided to add it for a little extra practice. What is the edge length of the cube? Because remember, a cube is a regular shape. All of the edge lengths are the same. So the volume of a cube is the edge length to the third power. So the edge length would be the cube root of the volume. Or in other words, the volume to the 1/3 power. Okay, so the length in this case is just going to be 777.8 to the 1/3 power. Oops. Raised to the, and you can say raised to the, okay, there you can see it. Raised to the parentheses 1 divided by 3 power, if you wanted it to be as accurate as possible. And we get 1.196. Let's look at the significant figures here. 2.1 only has 2, so we're going to be limited to 2 here anyway. Oh, that would be, the edge length would be only, would have to be rounded off to 780 with no decimal point for 2 significant figures. In this case, 9.2. And for the units, notice we had centimeters to the 3rd power, and then we took the cube root of it. So that brings it back down to centimeters. So a cube with 9.2 centimeters on each side should have a volume of 780 cubic centimeters. You could try it. 9.2 raised to the 3rd power is equal to, yep, 778.688. So that's close enough to what we got here within the number of significant figures anyway, that we can be confident we got it right. Okay, so you can go even further than what the book demands. 8 is about a cubic box containing 1,000 grams of water. Or in other words, 1 kilogram. What is the length of one side of the box in meters? Okay, and explain your reasoning. Well, the reasoning actually is going to be pretty similar to what we did up here. We have a cubic box, which means all of the sides are the same, and it contains 1,000 grams of water. That's the mass. The volume of the box is going to be mass over density. And so that's the 1,000 grams of water divided by the density of water, which is 1,000 grams per cubic centimeter. Or sorry, which is 1 gram per cubic centimeter. 1,000 divided by 1 is 1,000. And so 1,000 cubic centimeters is the volume of the box. Edge length of the box, again, is going to be the cube root of the volume, or the volume raised to the 1/3 power. So if you take 1,000 cubic centimeters and raise it to the 1/3 power, oh, well, yeah, of course. Shouldn't have had to do that on the calculator. 10. And cubic centimeters to the 1/3 power would be centimeters. 10 centimeters. But we're not done yet because it did say in meters. Okay, so 10 centimeters. And let's see, there's 0.01 meter for every 1 centimeter. Or you could say 1 meter over 100 centimeters. Works out the same way either way. Notice that centimeters cancel. You get M for the meters, in other words, for the unit. And 10 times 0.01 is 0.10. Okay, technically that should just be 0.1 because of the significant figures. 1,000 with no decimal point, that's only one significant figure. So 0.1 it is. Okay, let's see. 9. Is about a loaf of bread with a volume of 3,000 cubic centimeters and a density of 0.2 grams per cubic centimeter, is crushed in the bottom of a grocery bag, but that doesn't really matter, to a volume of 1,500 cubic centimeters. What is the density after crushing? Well, there's an easy way to do this question and a hard way to do this question. The easy way is to remember that that density is inversely proportional to volume if the mass doesn't change. Because remember the equation. D equals M over V. If you hold mass constant, then volume and density will change by the same factor, but in the opposite direction. If you double the volume, you cut the density in half because it's the same mass divided by a number that's twice as big. That gives you a result that's only half as big, and vice versa. If you cut the volume in half while keeping the mass the same, then you're dividing by a smaller number and the result is a bigger number. Okay, so notice here, the volume went from 3,000 to 1,500. In other words, you cut the volume in half. So the density should be doubled. It should come out to be 0.4. So by this logic, you can kind of reason it out and not even have to go through the math. But let's go through the math just to prove it. It's going to be 0.4. Okay. First, if you're going to do it mathematically, you need the mass of the bread. The only way we can find the mass is of the bread before it was crushed, because we have the volume and the density for that. Mass is density times volume. And before crushing, the density was 0.2 grams per cubic centimeter times 3,000 cubic centimeters. And that would be 600 grams for the mass. 0.2 times 3,000, just to make sure. Yep, 600. Okay, the mass should not be changed by the crushing. You're just basically pushing the little bread particles closer together, but mass is the amount of matter that's in an object, and you're not tearing the bread apart. You're just making it smaller by crushing it. So the mass should stay the same. Okay. Okay, so the mass stays the same. After crushing, density is going to be equal to mass divided by volume. And the mass is still 600 grams, but the new volume is 1,500. So 600 divided by 1,500 is, what do you know, 0.4. So just as we suspected. Now, we could do this easily without the math, because the density or the volume changed by such an obvious factor, cutting it in half. If it were some other factor, then you'd want to do the math, definitely. Number 10. What volume of copper would be required to balance a 1 cubic centimeter sample of lead on a 2-pan balance? Now, and a little translation might be in order here. In other words, what volume of copper has the same mass as 1 cubic centimeter of lead? That's what's really being asked, because we're saying they're going to balance each other out on a 2-pan laboratory balance. That means that they must have the same mass. We know that we've got 1 cubic centimeter of lead on one side, so we can find out, we can look up the density of lead and find out what the mass of 1 cubic centimeter of lead is. And then we can use that mass to find out how much copper it would take to make that mass. Okay. So first step, okay, mass is going to be density times volume. The density of lead, according to the table or Professor Google or Wikipedia or wherever you want to look it up, is 11.4 grams per cubic centimeter. And if we've got 1 cubic centimeter, I'm guessing that's going to come out to 11.4 grams. So that's the mass of lead. Now we need to know what volume of copper has that mass, 11.4 grams. Volume, if you look at the old density triangle, volume is mass over density. The mass that we found was the mass of lead, but we want the mass of the copper to be the same. So now this is going to become the mass of the copper. And the density of copper is listed as 8.96 grams per cubic centimeter. Okay, so 11.4 divided by 8.96, and that's 1.27 cubic centimeters. Notice that grams cancel, and cubic centimeters is on the bottom of the bottom, which is the same as being on top. So there's your volume right there. 1.27 cubic centimeters of copper. And that's all of the parallel exercises. The ones that I assigned to you from group B are very similar to these. So if you were having trouble with those, take these, look at how I did these, and then try those group B problems again, and hopefully you'll get it. I do have solutions for the group B problems, which I will post right after the deadline for handing them in. You'll still have your copy of it, so you can check yours against what I did for those problems. And okay, well, I guess that's enough for this segment of the video. See if I can find something to do for the next part.